What is it we mean when we say a reciprocal function? The phrase reciprocal function doesn't have any meaning unless we're talking about a particular function to begin with. Reciprocal functions mean we start off with an original function like perhaps 1b, and we can call that original function f of x if we like. It's equal to 3x minus 5. That is not a reciprocal function. What the reciprocal function is a new function. We could put y if we wanted to, but I like to use a different letter, g of x. G of x is equal to 1 over the old function. And what's very important that you understand here is we're going from, in this specific example, f of x equals 3x minus 5 to g of x equals 1 over 3x minus 5, which means we're going to g of x equals 1 over f of x. Okay, so what we're doing is we're going from y equals a function to y equals the reciprocal of that function. And what we learned yesterday, this was kind of the culmination of what we learned, was that in the end, on the original function, when you have a point, it turns into, on the new function, this point. It's all about y coordinates. And we did that through illustration with an example. But the bottom line is if you know the coordinates of a point on the original function, you can determine the coordinates of the point on the reciprocal function by just taking the reciprocal of the y coordinate and replotting it. That led to a number of different rules. Oh, let's just take one here. Let's say that if I know question 3 says what's the equation of the vertical asymptote for each function. But I'm going to say, let's say we wanted to sketch the reciprocal function f of x equals 1 over 5x minus 10. Unfortunately, it says f of x, and you might be more at ease if you change that to g of x, where the original function was 5x minus 10. But the bottom line is, if I ask you to sketch that function, you start off by sketching instead y equals 5x minus 10. So how do you sketch y equals 5x minus 10? It's a linear function. The y-intercept is negative 10, and the slope is 5. So that would mean it would pass through negative 10 here. It would have a slope of 5, so it would be going over 1, up 5, over 1, up 5, which means, everybody, by the time it reached the x-axis, it will cross at 2. Which, you should know the x-intercept is 2, because if you take this function and set y equal to 0 and solve to find the x-intercept, you're going to get 2. So that's what the original function looks like. And there's some place here where y is 1, and there's some place where y is negative 1. Don't worry about the fact that I don't believe I've scaled that very well. Okay? So there is some point right here on the original function. And you know what? I don't care what the x-coordinate is. When I now start to plot 1 over, I remember that this is what happens. All I have to do is say, if I take the y-coordinate of this point, which is 1, and I take the reciprocal of it, what do I get? Well, I get 1. So that point is invariant. This point will not move. Down here, the y-coordinate is negative 1. What's the reciprocal of negative 1? Negative 1. It doesn't move. What is the y-coordinate right here? Well, it's 0, right? What's the reciprocal of 0? Yeah, the good way to put it, Seamus. That's what it is. It doesn't exist. You can draw that on an exam. But what we actually draw on the graph is that vertical asymptote. And right away, we've actually answered question 3 in terms of what it actually was, right? Question 3 said, determine the equation of the vertical asymptote. Well, the equation of the vertical asymptote for question 3a is x equals 2, because it's where the x-intercept of the bottom of the thing is equal to. The bottom of the function is 5x minus 10. You set 5x minus 10 equal to 0, and you solve this to find. Remember yesterday some of you said, well, what is a non-permissible value? That's what it is. It's the value of x that's not allowed. Generally speaking, then, the rest of the graph will look like this. And you also have to know that there is a horizontal asymptote there. So the steps that I gave you yesterday as a summary were aim. Put in your asymptotes first. So you will always have a horizontal asymptote on the x-axis in this course. You will always have a vertical asymptote wherever the original graph touched the x-axis. Then put in your invariant points. That's where y equals 1 or negative 1. They do not move. Then do motion. And basically, if the original function is increasing, whatever you draw has to be decreasing. With this, you really should be able to, well, with that combined with this idea, you really ought to be able to sketch the reciprocal of any function if you can see the graph of the original. I'll give you an example here. And then we can get to the questions, and then we finish off the unit. So I am going to sketch a function. There are my axes. I don't know what the equation of that is, and it doesn't matter. You should be able to sketch the reciprocal of it. What will the reciprocal look like? Well, aim. A means asymptotes. The x-axis is always an asymptote, and you will have an asymptote wherever there's an x-intercept. A classic question in 30-1, although we don't deal with reciprocal functions, we deal with other things, is how many invariant points. So this thing that I've drawn is y equals f of x. I'm going to draw in green y equals 1 over f of x. And the question I'm throwing your way, and it's a good exam question even in this course, is how many invariant points will there be? Kendra, do you know? There will be 4. Because you're going to look wherever y is 1. Because the reciprocal of 1, don't forget, this is what's going on again. You're going from x comma y on the original function, and all it changes to is the same x-coordinate, but the reciprocal of y. And when you take the reciprocal of a y-coordinate of 1, you still have 1. When you take a reciprocal of negative 1, you still have negative 1. So here is y equals 1. You can see that over on the left, there is a point here with a y-coordinate of 1. There's a point over here with a y-coordinate of 1. And you know what? I've done something here that maybe I shouldn't. I shouldn't end this. That gets a little complicated. I should put arrows. You don't know what to do if it ends, and I don't want to confuse you. So those points won't move because when you take the reciprocal of the y-coordinate, that won't change. It will still be the same y-coordinate. Same with this point where y is negative 1. This point where y is negative 1. They won't move. So what you're going to have up here is some curve that looks like that and some curve that looks like that. you have to have some curve that looks like this somehow, and here as well. What we're going to learn today is what you do in here, and it's not difficult. You would just take some key points like this, which is maybe at -4, and you'd take the reciprocal of -4 and get -1/4. And then maybe you would take this point, which is -3.75, and take the reciprocal of that, and it would be maybe here. And you would take the reciprocal of this y coordinate, and it would be maybe here. And what you would end up doing is building some kind of graph. I kind of skidded into the dirt there on the end there. It should be going through that invariant point, so I'd better sketch that again. You would get some graph after picking some key points that would look something like that. But you're just taking y coordinates and reciprocating them. That's all. Everything else falls into place. So now let's take a look at your problems from yesterday. Does anybody have any questions from the practice problems? Go ahead, Seamus. 10A. So we are asked to determine the original function. So what this is a little confusing. This is the reciprocal of the original function. This is what we get if we knew the original function and put in the asymptotes and the invariant points and sketched it. So we want to work backwards. Well, remember that a thing that is reciprocal of another thing means that they're reciprocals of each other. So I don't even want to write 1 over y. I just want to say that whatever the y coordinate on the original function is, the reciprocal of that gives you a y coordinate on this function. And whatever a y coordinate on this function is, the reciprocal of that takes you back to the original function. Which means that if on 1 over f of x we have a point of 4, 1, then on f of x we have to have a point of 4, the reciprocal of 1. And I feel a little silly writing that because since y is 1, it's invariant. In other words, the equation, the graph of the original function will indeed pass through 4, 1. I want to make this a little bigger. The graph will go through 4, 1, the original graph. Now, this hasn't been pointed out to you, but do you see the general graph that you're looking at here has two curves? Whenever you have two curves like that that are in diagonally opposite regions, that is a reciprocal of a linear function. Anytime you have a straight line at an angle, you're going to get this kind of picture. Now, the two curves may be in the top right and the bottom left, or they may be in the top left and the bottom right. It depends, but this is going to be a linear function. We know the original function has to pass through here because this is an invariant point, because y is 1. By the way, if this were, and it's not, but if this were 4, 2, then the new point, or the original point, would be 4, 1/2. If this were 4, 1/2 on the reciprocal function, then the point on the original function would be 4, 2. We're just reciprocating y. But since the y coordinate is 1, this point not only is on the reciprocal, but it's on the original. Now, the other thing is we know that wherever there's an x-intercept on a function, you get a vertical asymptote. And that means that that line whose equation we're trying to find must also pass through the x-axis at that point. And we could certainly draw the line now. And what this problem has turned into is a grade 10 coordinate geometry problem. How do you find the equation of a line? You use y equals mx plus b. We can see the y-intercept is -3. So this is going to be y equals the slope times x minus 3. You can see, I think, most of us, by looking at it, that the slope is 1. You go over 1, up 1, over 1, up 1. If you wanted to make a triangle here, say from here to here, your run is 1, 2, 3, 4. Your rise is 1, 2, 3, 4. Your slope is rise over run. Which is 1. So there's the equation of the line. I think ultimately there are more algebraic ways to do it without actually sketching the line, but I would recommend, if you see this, and you would on the exam next week, you draw the line so you can just see what the y-intercept is, and so you can calculate the slope. Is that okay, Seamus? Yeah. Okay. Does anybody have any other questions you would like me to go over before we get started today? Yeah.
I'm just curious as to how one of these would work into a word problem.
So am I. I can't think of anything. This is pure math now. This is not some kind of applied math that we would use this for. I think I could make up a word problem, but it would be what I call in high school math contrived. It would be a phony question that I made something up and I added words to it, and I said something like the water pressure in a tank is given by this. I would just be doing this. Okay, I'd just be making stuff up. So I wouldn't worry about word problems here. Probably on the exam, and we're a few days away from the exam, we still have to finish the unit and do a couple days of review. I think this would be a good written response question. Not this one in particular, but in this section, where I maybe give you a graph of a function and I say, okay, draw in the vertical asymptotes and the horizontal asymptotes of the reciprocal, and sketch the reciprocal function, and find the y-intercept of the reciprocal function, and all of that. Because, just on a side note here, if you want to find the y-intercept of the reciprocal function, since the reciprocal function always reciprocates y, just find the y-intercept of the original function and go 1 over that, and that will be the y-intercept of the reciprocal. So, for example, this y-intercept here is -3. This y-intercept is going to be -1/3 because it's the reciprocal of -3. I can see you're all raring to go here on the next lesson. Reciprocal functions part 2. So the only thing that is going to be different here is that we are looking at graphing reciprocal functions of quadratic functions, not of linear. So I don't know, I just had to erase something on mine, but does yours say just quadratic? It makes reference to it. So that's what we're doing today. And we're going to dive right in. First example, if y equals f of x and the reciprocal is y equals 1 over f of x, so let's just stop for a second. That statement up to where it says 1 over f of x, that's every question we've been working on in this section. Y equals f of x is the original. Y equals 1 over f of x is the new function. In this example, the original function is x squared minus 5. In the example I was talking about earlier, I think the original function was 5x minus 10. Does that ring a bell? That was a linear function that we were reciprocating and graphing. This is a quadratic function. So graph and label each of the functions. So first of all, let's be very clear here that the original function is y equals x squared minus 5. And the new function is y equals 1 over x squared minus 5. if you want to, impress your friends and family, you can use function notation here, and you can say, well, f of x is x squared minus 5, and g of x, the new function, is 1 over f of x. And I'm when I say impress your family and friends, I'm kind of trying to be a little sarcastic, but in all seriousness, this is a little more sophisticated. This is important because it illustrates the difference that the y-coordinate of the first function, this is the y-coordinate of the first function, is different, I don't know what's going to happen here, there it is, than the y-coordinate of the second function. But when you look one line above, they're both y equals. And somebody who doesn't understand what's going on might think that the y-coordinates are the same. They're not the same. They change. So let's start off with sketching y equals x squared minus 5. This is a pretty simple one to sketch. Don't draw anything yet. I'm just pointing out to you. In fact, I'm not going to draw it on here. You should know that x squared minus 5 starts off with y equals x squared, whose vertex is at the origin, and it shifts down 5. So you should know that this is what it looks like, generally speaking. But we've got a grid, so we want actual points. One thing we do know is that the y-intercept of x squared minus 5 will be at negative 5. We can use our skills from previous units. I'm talking here about y equals x squared minus 5. And we can find the x-intercepts by letting y equal 0 and getting 0 equals x squared minus 5, shuffling that negative 5 to the other side, taking plus or minus the square root, and then, saying to ourselves, well, what's the square root of 5 approximately equal to? Because we want to be able to plot these x-intercepts. And I want to say it's about 2.2. Close enough for what we're doing? Okay. So we are going to have an x-intercept. Ooh, this is a sneaky scale, isn't it? Is your graph different?
No, there's no 5 below the x-axis.
Thank you. There's a problem with the scale. Is the problem on yours as well?
Yeah, it just goes 1, 2, 3, 4, 6.
Yeah. This 6 should be a 5. And the 7 should be a 6. So yours is wrong as well? Yeah. Okay. I got to fix that for next time. So this is negative 5 here. This is negative 6. So the y-intercept is at negative 5. Thank you, Kendra. So the x-intercepts are positive root 5 and negative root 5, and we said that's about 2.2. So 2.2, 2.5 is here. So 2.2 is 2/5 of the way there. This doesn't have to be perfect. Now you can get more detail. I think you might be in trouble if you just try to draw this from these 3 points. You know something about y equals x squared. Y equals x squared goes over 1 and up 1, over 2 and up 4, over 3 and up 9, etc. So we can use that same pattern. We can use that same pattern. I think I'm... We can use that same pattern here. Here are my points. I was using the grid for the next example. Here are my points. Looking at the y-intercept, we can go over 1 and up 1 on both sides. We can go over 2 and up 4 on both sides. We can go over 3 and up 9, except it's not. I got to change this graph. I hate this scale. Over 1 and up 1 takes you to here, doesn't it? Over 1 and up 1 on the other side takes you to there. Over 2, I got to change this scale. This is driving me nuts. Takes you to here, and up 1, 2, 3, 4 takes you to here. So now at least you have some more points that you can deal with. Although I think I'm getting sucked into doing some stuff here that really is unimportant in the big picture. Those are what the points look like with y equals x squared minus 5. And again, it's that crappy scale that I've chosen to use for this graph. So this is what y equals x squared minus 5 looks like, very approximately. And I always, when I draw these, end up drawing it a little too pointed at the bottom. So if you do the same thing, it's not a big deal. So how do we draw? Just fix this a little bit. How do we draw the reciprocal? Very easy. Very easy. Aim. Let's draw in the asymptotes first. I'm going to do my reciprocal in red. So we are going to have a horizontal asymptote on the x-axis, and we are going to have a vertical asymptote wherever the graph crosses the x-axis. And now, we talked about this yesterday, you're going to need a very sharp pencil for some of this. I'm going to have to blow this up quite a bit. In fact, I'm going to make these asymptotes maybe a little thinner so that you can see them a little better. So those are the asymptotes. Are there any invariant points? Yes. There's an invariant point here and here. Why are those 2 points invariant? Why are those 2 points that I indicated in red not going to move? Yeah. Right, because y is equal to -1 at those 2 points, and if y is equal to -1, the reciprocal of y will be the reciprocal of -1, which doesn't change. I will also have 2 invariant points, and I'm going to draw this parabola a little bit further in both directions. I will also have 2 invariant points here and here. And I think you know what's going to happen. I'm going to blow this up. Over on this side, I'm going to change my mind and draw green. There's too much red there. We are going to have, I wonder if my computer is going to survive this. We are going to have a curve which I'm hoping is going to pop up here soon. There it is. And then over on the right-hand side, we are going to have a curve that does the same thing. And what I'm doing to get those 2 curves is I'm saying, in this corner, between these 2 asymptotes on the left-hand side, in that corner, going left to right, the original graph is going down. It's going from here to here to here. It's decreasing, which means the reciprocal has to go up. There's only one way to draw a curve that's going up. If the curve is, get ready for it, this is a word, if the curve is asymptotic to both of those asymptotes. And it's to draw what I've just drawn. Asymptotic means it's got to get closer to them. And the same thing is true on the other side. Now, what do we do in the middle? I'm going to go down one zoom setting here for us. What do we do in the middle? I'll have to wait. Well, we have to start picking some key points. I want everybody, while I'm waiting for my computer to catch up with me, I want everybody to find the y-intercept of the reciprocal function. There it is. It's caught up. This original point is at 0, -5. Don't forget the reciprocal function is found by taking the reciprocal of y, which means the y-intercept will be at 0, -1/5. So 1/5 is a fifth of the distance between this x-axis and this -1. So it's approximately here. Approximately. Now think about this for a second. Don't sketch this next part. Just think about what I'm going to say and draw. From, and don't mess up your graph, from point 1 to point 2, the original function is going down. The reciprocal must be going up. So the reciprocal must be, in general, climbing, 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 and then from point 2 to point 3, the original function is climbing. It's going from -5 to -4. It's climbing, which means the reciprocal has to be decreasing. So that's what we have to draw in here. Now, how accurate it turns out to be is not important. What you're going to have, let me get back to, there we go, is the following. It's going to go up, so it's asymptotic as it's going down against the asymptote. It comes up to that peak, and then it's going to continue to decrease afterwards. And that's what the reciprocal of that quadratic function would look like. Any questions with the graphs? All right, we do have some other things that we need to do here. It says, what is the domain and range of each of the functions? What are the equations of any asymptotes? And what are the intercepts? Well, we can put the intercepts right on the graph. Well, no, you know what? It's pretty crowded. Let's do it this way. F of x, the y-intercept is -5. The x-intercepts are plus or minus √5. The domain is any real number for x. We're looking right now, everybody, when I say f of x, we are looking at the brown graph, right? The range would be y is greater than or equal to -5. What about 1 over f of x? I guess I'll draw that in green or write it in green. What about y equals 1 over f of x? Well, there aren't any x-intercepts. In fact, this is something you should have discovered in yesterday's practice stuff, is that reciprocal functions don't have any x-intercepts. Not in this course. The y-intercept would be -1 over 5. What's the domain? How do we write the domain? Well, what I'm going to do is write that x is not equal to something. What can x not be equal to? James? On the green function, -1 for x does have a point. I'm talking about x coordinates here. Yeah. Plus or minus root 5. So where the x-intercepts were now become not allowed. You could put for the domain, this is really clunky, -infinity to -root 5, -root 5 to root 5, root 5 to infinity, all with round brackets, which means you never equal the -root 5 or the root 5. I think it's so much easier to just say x cannot equal plus or minus root 5. The range, oh, that's a tough one. This is a tough one. And this is, maybe we're doing the range here just to keep our brains sharp. When you look at the green graph, y is always greater than 0. It's above the x-axis. It can never equal 0. But we also have this part down here where y is less than or equal to -1/5. That's a weird range. There's two pieces to the range. There's the piece above the x-axis and there's the piece below the x-axis. By the way, the asymptotes, this asymptote is at x equals -root 5. This asymptote is at x equals +root 5. Your domain statements say x is not equal to those numbers. Your asymptotes tell you where those asymptotes exist. A lot going on in that question, but the basic idea is AIM, asymptotes, invariant points, motion. Let's try another one. My computer is really sluggish. Sketch the graph of x squared plus x minus 6. Label that graph and the reciprocal. I don't think we need to go through as much detail in this example with domain and range and everything. Let's sketch x squared plus x minus 6. If we factor this, we can see what the x-intercepts are. They're the values of x that give us 0 for y. Which means an x-intercept is at -3, and x-intercept is at +2. That also means that's where we'll have vertical asymptotes for the new function. So it's going to cross at -3 and at +2. Just by inspection, you can see the y-intercept is -6. Do you have the same issue with your graph? So that 6 becomes a 5. It isn't? So the 6 becomes a 5, the 7 becomes a 6. Now, be careful here. This is really not that important, but I hope you can see that that y-intercept is not halfway between the x-intercepts. Halfway between the x-intercepts would be along this line, which would mean the vertex is someplace lower than that. Doesn't have to be exact, but I just don't want anybody drawing this. It doesn't look like that. It has to go lower. And I find if I have a point in there to use, it makes my life a little bit easier. Good enough for what we're doing. There's the original function. I'm going to show you what the reciprocal will look like if I really don't care too much about accuracy. Okay? I guess I should go to a bigger view. Maybe what we should do first of all is find the y-intercept of the reciprocal. The y-intercept of the original function is -6, so the y-intercept of the reciprocal is -1/6. That's pretty close to the x-axis. Very close to the x-axis. I'll go to a bigger zoom now, at risk of crapping out my computer. While I'm waiting for my computer to catch up, perhaps you can do me a favor and indicate where the invariant points are going to be. There it is. You're going to have an invariant point here and here, because those two places have y coordinates of 1 and -1. You're going to have invariant points here and here, because these 2 points have y coordinates of 1 and -1. So now comes the part where I'm not going to worry too much about accuracy. I don't have to take y coordinates in these 2 regions and reciprocate them and replot them. That's what it's going to look like. I know that this piece must go up towards the center. The y-intercept was -1/6, which is very close. However, and I don't know if we need to worry too much about this, however, since the y-intercept wasn't the lowest point on the original graph, that y-intercept that we found by reciprocating it won't be the highest point on the reciprocal. If you knew this y coordinate here, maybe it's -6.5, then the reciprocal of -6.5 will be even closer to the x-axis. And all I am getting at is that at this location horizontally is where the graph has to peak. It has to peak at that point because it's the lowest point. So when you sketch this, it looks something like that. We don't need to go through domain and range and all of that. I think you get the idea. Any questions with that example? By the way, it's going to be very easy for you to confuse now that you have absolute value functions where you fold stuff up and reciprocal functions where you do all this madness. It's going to be very easy for you to mix them up from time to time. If we take a look at the next example, we're not going to do the next example because that is an example from yesterday's lesson. We did that yesterday. So we're going to go to the final example here. Seamus asked a question when we went over the homework that was like this example where we had to work backwards and find the equation of the linear function. Question 4 is asking us to work backwards to find the equation of the quadratic function. So this is a really simple kind of question, actually. Since there's an asymptote on the reciprocal, this is y equals 1 over f of x. Since there's a y-intercept on the reciprocal of negative 1 over 12, the y-intercept on f of x, the original, has to be at 0, negative 12. We don't have room to plot that point. But we should make a mental note that whatever quadratic function we come up with, it has to have a y-intercept of negative 12. We know that there's an x-intercept at negative 3 on the original, because wherever there's an x-intercept on the original function, it becomes a vertical asymptote on the reciprocal. So we have x-intercepts on f of x equal to negative 3, 0, and equal to another one at 4, 0. And this, again, this is really not a difficult question. If you have an x-intercept of negative 3, then the quadratic function has to have a factor of x plus 3. It has to. And if we have an x-intercept of 4, the quadratic function has to have a factor of x minus 4. The only question that remains, that function that I've just written will have the proper x-intercepts. Will it give us a y-intercept of negative 12? And if it does, then we're done. And it does. How many of you see that you get a y-intercept of negative 12 because if you FOIL that out, you get minus 12 at the end? Okay. How many of you see that you get a y-intercept of negative 12 because if you make x 0, you have 3 times negative 4, which is negative 12? Fewer people. Anyway, this is the answer to the question. F of x equals x squared minus x minus 12. When you FOIL it out, you're going to get negative 4x plus 3x. And we've come so far in this course, I don't think I need to write that. It's negative x. Now, what if this was negative 1 over 24? So we're done. You don't need to worry about writing this down. But what if it were negative 1 over 24? That would mean that the y-intercept of the reciprocal is negative 24. The y-intercept here is not negative 24. How could we make this y-intercept negative 24 if we had to? Seamus. Exactly. Multiply the whole equation by 2. That's not going to change the zeros of negative 3 and 4. It's just going to change all of these to a 2x squared, a 2x, and a 24. So I don't know that you would ever encounter that in this course, but we're certainly going to be leading up to it in Math 30-1. Let me go back to reality here. So any questions with that final example? It's not 1 to 10. Included in 1 to 10 are all the questions that were linear reciprocals, which you worked on. God, is today only Monday? Today's Tuesday. Oh, okay, good. Which you worked on yesterday. I thought, oh man, I lost the day somewhere. That's good though. Which you worked on yesterday. So the ones I've got outlined up here are the ones in that section that deal with quadratic functions and their reciprocals. And the reciprocals of quadratic will always have 2 little curvy parts and 1 little hump. And it will look like this green thing if the original parabola opened up. If the original parabola opened down, then everything would be upside down. The 2 curly parts would be below the axis and the hump would be a valley above. Anyway, you've got some practice to do here. Tomorrow we'll get started on some review, which we'll do tomorrow and Thursday, and then exam, once again, is Monday. So get to work on that, please.